Continue this afternoon's session with Paul Bressler, who was a student of Raúl Bott.
Why?
That's very remarkable. It's very important.
Really? You've never seen a student of Raúl Bott before?
So your title of your talk is?
I forgot.
It is comparison of spaces associated to differential graded Lie algebras via higher holonomies.
Yeah.
Thank you.
Okay. Well, it's a pleasure. Thank you for invitation. It's a pleasure and a privilege. So yesterday I made the plan. Which consisted of two parts. Well, I'm afraid one was part one would be like I have to explain what the problem is, and part two is the solution. I must admit that after I wrote 10 pages of notes about the problem, I have some suspect that part two we might never get there. But this might be okay. So the problem, so as it says in the title, so I'll explain what remind you what differential graded algebras are quickly. So then there are these nilpotent ones of interest. And then there are two spaces in the sense of, I guess, there is the set of Marek-Hartan elements. I'll explain about this. Then as a result, there will be, first of all, a space simplicial set, meaning called this. It's quick. Then there is a two groupoid, which I'll explain what that is partially. Then this will have, well, at least what's called a simplicial nerve. Well, the goal, basically, what do we want is a map. I will call it I, because from the word, I guess, integral, maybe, in between with various properties, but homotopy equivalence. So this is the problem, and the solution is how one organizes for that, but we'll never get there anyway, so it doesn't matter. This is similar. See, if you change this around a little bit, it's like E equals MC squared. So result previously known, you know, Einstein, but then you see they're not very different from that. All right, so I will, okay, I can leave this here and start down the list. So differential graded algebras, we have, well, it's a complex, I guess, which for me is a cohomological notation. Differential raises the degree. So there is the differential, I'll write delta, maybe. And then the bracket. One has to remember the signs, of course. So, and the differential is the derivation of the bracket of degree 1 and square 0. All right, so nilpotent means that the algebra is nilpotent. I mean, you have a lot of brackets, all 0. Right, so the examples of this, not necessarily very nilpotent at first. Well, for instance, abelian. Well, so there's no bracket, it's just a complex. We heard yesterday Camilo's talk. It's like the situation, it's bad notation, but to me it's the situation similar to this. So what I mean is, it lives only in non-negative degrees. This is like linear algebra. In a sense, I can maybe explain later. Okay, so this is more familiar. Now, the kind of Lie algebras I'm interested in, maybe it would be something like this. You take if you have an associative algebra over a field of, say, characteristic 0, then people like this. You take the Hochschild cochains shifted by 1 plus this has a differential and what's it called, the Gerstenhaber bracket. But this Lie algebra, it starts in degree -1 as opposed to this. Because this is not about deformations of linear structures, it's about formations of algebra structures. Another maybe example is if you have a Lie algebra, again, then I guess you form something similar. You have Lie cochains with coefficients in the itself shifted by 1 with a Gerstenhaber-like bracket. And various deformation complexes of various algebraic structures, they all look like this, also has this property, starts in degree -1. But these don't appear nilpotent, and they're not. But typically in formal deformation theory, you end up, so these are not nilpotent, but to make them nilpotent, you do this. So you have a commutative arc in algebra such that, say, M, and this is the maximal ideal, and such that, I don't know, there's some nilpotency length, and you look at then this. Like in these cases. But it won't be important. So for us, just the nilpotency condition. So what does one do with this? All right, so let me preceding list. So if you have a, so this is nilpotent differential-rated Lie algebra. So one has the set of Cartan elements, so the elements of degree 1, satisfying the equation which actually, if you prefer, is supposed to mean this. After division by 2. So in other words, this is like a connection 1 form. And this is the flatness condition. All right. Okay, so for instance, by the way, so if you have, say, A in abelian Lie algebra, then I guess MC A, well, in this part disappears. So this is just cycles of degree 1. All right. Okay. So now I'm going to organize all of this in a simplicial set. use of. So this is the standard, I guess, trick. So let me introduce these omega n. So these are polynomial forms on simplest of size n. So you take your, well, we can take our field here. You have variables x1, maybe t1 through, oh, sorry, t0 through tn, and variables dt0, dtn, satisfying the relations, well, sum of ti is 1, sum of dti is 0, and the derivative, and there is d such that d of ti is dti, and dti is 0. So there are polynomial forms on a simplex. Well, simply there is some affine subspace. Okay, so, all right, well, I mean, then what do? You take your Lie algebra, multiply, it's a good question, oh well, say, y forms, and, well, if this was nilpotent to begin with, then so is this algebra. But if you multiply a Lie algebra by commutative algebra, still a Lie algebra, differential graded, where differential obviously includes the exterior derivative, and you take MC over that, Mercaton elements, and you call that sigma n of G. Right, so this is actually, I guess, a simplicial object in commutative algebras, and this is a simplicial set as a result, and maybe familiar in rational homotopy theory, I guess, and maybe we can have, well, some sample calculations. For instance, if, let's say, A is a billion, then what is sigma A actually? So it's more or less, well, it's one version of K A. So to any complex, you can associate this, so to speak, Eilenberg-MacLane space. The shift has to do with that. Remember, these were cycles in degree 1, in degree 0. And here it's normalized differently. And this is like a differential form version of this. And there is even a map called integral, well known to be a homotopy equivalence. Well, maybe let me mention it now. So A is an abelian object. So this is a group. This is a group, and this is a group homomorphism. This, of course, is defined, instead of forms, you use, I guess, chains on combinatorial cochains. And so it's much smaller. And indeed, I mean, many things integrate to 0. But this is much, much worse. Okay, well, we have sample calculations also. So first of all, I mean, in degree 0, we didn't do anything, so this is the old set of Mercaton elements in G. Also interest, so maybe I should have dot degree 0. What's maybe instructive to look at what happens in degree 1 once. So I tried to calculate, but I may have screwed up some signs. Sorry. So, well, what is this? So this is supposed to be, you take G times forms in one variable, essentially, right? It takes what's in degree 1. Sorry. So what does that look like? So you have, let's see, so you have, oh, this was a big mistake. Okay, this T is not one of those. This T is T0 and T1 modulo this relation. Let's say T1, right? So there is this much in degree 1, and what else is there? And then there is the 0 degree part, which is use a form. Right? So we can compute what the condition means. And so here, I guess, the face maps give evaluation at 0 and evaluation at 1. But this part dies, of course. Here you just get values at 0 and at 1. Okay, so, well, I mean, so let's say I take A of T plus B T dt. So, and you, so let's differentiate first. So, okay, well, delta A, maybe I'll skip T, plus A prime dt, I mean derivative. Well, you cannot differentiate this further, but you can do delta B dt. Right? Okay. How about you bracket this with itself? Well, basically, this with this is 0 because dt squared is 0. And the rest looks more or less like this. So A, B. I mean, these are Lie algebra valued functions plus 2 times A, B, dt. Oh, A, I'm sorry. A. And we have to remember that this is not 0 because A is degree 1. So it doesn't have to be 0 at all. Okay, so half of this plus this should be 0. Right, so MC is, let's see. So first of all, what do we see? So that A, so this is 0 and so in degree 0 we have, so in the function part we just have this. So delta A plus half of all of this is 0. Right, so A of T is just like a family of Meyercartan elements. And then the rest says that A prime plus, so half of this is just AB, is 0. So it's your typical ordinary differential equation. So that's all there is to it. So Meyercartan element here is, so it's a family of Meyercartan elements, satisfying differential equation. Now the boundaries, so to speak, conditions, and solve. And so the value at 0 and the value at 1, I guess, are related if you know how to solve ODE.
What happens to delta B?
Where is delta B? Where? Yeah, where did that go? Ah, no. I just pulled out dt. Ah, this. Where did it go? A prime plus delta b. Right. Where's this? I guess. Yeah. I would prefer somehow to write it down in some different way. Okay. Where did that go? That's right. Well, something. Right. But in general, I mean, it's similar situation for higher dimensions, right? You have a big simplex, and on it you have this A, and there is some, differential equations, and there's like a connection, but more comes in. I'll write it out later. Okay. Yes. Now, yeah, okay. So now it's instructive to look at, see here in dimension 1 simplex, you don't see the unfortunate possibilities. So let me try another calculation, but basically for n equals n, what you see is this, right? So sigma n is a subset of, well, it's g times forms in degree 1. But that is much more complicated now. I mean, there is g1 times 0 forms. Well, these are just functions, like polynomials in T. Then there is g0 times 1 forms. Okay, so these are some kind of functions. This is like 1 forms with matrix coefficients. It could be a connection like before. But then there is more. This is a 2 form. You start thinking curvature level. Were related, right? And in principle, more and more. Of course, in the situation of yesterday, there is none of this, simply. In my situation, there is none of this, at least. Again, as a homework exercise, one can make more successfully than I just did now. You write out what it means to be a Manhattan element. Right now, maybe it's not that important, but so it's some. But basically, it's kind of the same. So you have a family of Manhattan elements. Then there is a connection, 1 form. And the connection is not flat anymore. And this 2 form is related to its curvature in a certain way. Okay. So that is roughly what that looks like. So what to do? So that, I mean, so this is so this simplicial set was, I think, originally probably appeared in work of Hinich, where he always likes to deal with differential grading the algebras. But this makes perfect sense for any nilpotent L infinity algebra. So I think Erick Tovar liked it. And in general, this is, well, if you have more here, this is not clear at all what this means. It is a homotopy invariant of G, however. Okay, well, yeah, so which brings us to this, the other half of the equation, the MC squared part. So I'll try to describe what this is supposed to be, but closer to the Eilenberg-MacLane space picture. Okay, so, well, okay, so this is actually the strict two-groupoid in the sense that, I mean, there are objects, morphisms form groupoids, and everything's just perfectly fine with it. Okay, so we already had MC. So I'll describe first groupoid MC1. And so objects are MC. So the nice thing is that these, well, the infinite dimensional kind of component on the force doesn't even enter. I mean, I'm not saying this is a small set, but so the object are this set. Now, what are morphisms? Well, not something that is possible, I guess, in the L infinity picture, but here, G0 itself. I mean, it is a Lie algebra, in fact, nilpotent Lie algebra, in the usual sense. And so there is a unipotent group, which I guess is. So this is, as a set, is the Lie algebra, and you multiply using Campbell-Hausdorff series. And so this group, I mean, it acts on everything, including G1. For instance, and on the subset of G1, which is the subset of Mayer-Cartan elements. But the action, you have to understand, this is like by gauge transformations, in the sense that I mean, there's a complicated formula I don't want to write down, but basically G delta plus gamma G inverse. As usual, gauge transformations act on connections, because gamma is a connection form. I mean, I can write down the formula, which probably is. Well, you have to write down the formula in terms of an element of this, in some series. All the series not just converge, I mean, they're finite, because they're all iterated brackets, so it's no issue. Okay, well, so MC1 G is the, well, if you have an action of a group on a set, you have a groupoid, right? So I guess they call this action a groupoid. Okay, so objects are Mayer-Cartan elements, and all of maps is all of this times the group. Source and target are projections and the evaluation of the gauge transformation. Okay. So if you don't have anything in negative degrees, this is it, essentially. And is known that it's also a homotopy invariant. Of course, the set itself is not, obviously. But the groupoid is meaning equivalent Lie algebra is equivalent groupoids. However, if you have the part in degree -1, this is obviously wrong to do. So you need to bring that in as kind of a relation on this in the form of two morphisms. So these, I really don't want to describe this explicitly. Well, but in rough terms, it's like this. So if G greater than or equal to 0, we're done. I mean, you can consider a groupoid as a two-groupoid where all the higher morphisms are just identities. So for G greater than or equal to -1. Well, roughly speaking, the following happens. So you have this G -1, there is G0, and here is G1, And here we have a Mercalli element. And this is delta. Well, if you look at this part, I mean, what's a Lie? This is a Lie algebra. I mean, it's a little bit abelian, but it's a differential graded Lie algebra in degree 0 and minus 1. What is that? It's otherwise known as, I guess, a crossed module. So what you do is this. So you can, and now we can, I don't know how to denote this. You take G minus 1, I'll write gamma. So you put on this the derived bracket. Normally you would, I'll write down the formula. Normally you would do it with just delta, but I am allowed to, see, the point is this, I can use this differential now. So derived bracket looks like this. So A, B, well, this is for A and B here. So normal bracket would put you in degree minus 2, and there is nothing there. No, you go, I guess, A, and then you apply this nonsense to B. And this is bracket in G. Hard to believe, but it is a V bracket on this. And you get yourself another nilpotent Lie algebra. So you exponentiate that and use it to act on these. On morphisms here.
So applying gamma means?
Yeah, this is just bracket with gamma. Yeah, it's not unknown. To work? Right. I mean, I might have screwed up signs somewhere, but more or less, they say it is correct. All right, so you exponentiate this Lie algebra, and you write down the formula, which I don't want to write down. So action of it on morphisms in this groupoid, and you get yourself, and so the home in, right, so home in MC squared between gamma 1 and gamma 2, that's supposed to be a groupoid. So this is the, well, it's basically, so morphisms are this group which varies. So this is action of, I guess, X G minus 1 gamma 2 on arrows from gamma 1 to gamma 2. Unpleasant formula involving some series, which let us not. Well, basically, these are like automorphisms. You actually multiply these on the left. Right? That was more like conjugation. So of different characters, one-sided multiplication. Okay. So anyway, so this is a groupoid. So you can check that the whole business is a two-groupoid to write down. And this is known, I think, as Deligne groupoid. One can say 2, which was, however, apparently rediscovered by Professor Gitler, how do they say it, later, but independently. But we just say Deligne groupoid. Okay. So then next question comes. So this is just a groupoid, and how to make it into a space. So because this, so if you're familiar, so this in higher category theory, so they have the simplicial nerve, which I'm not going to try to explain. So that is applied to simplicial groupoids. So because this is a strict groupoid, so you make it into a simplicial groupoid like this. You take the home groupoids, take their nerves, and now at every level of that you have a groupoid. And so with the same objects. And so it's a simplicial groupoid, then you do whatever you have to it. And I'll tell you what the answer is. It's kind of intuitively clear that this is it. Or it should be. Think maybe, I don't know who was first in this. I could say Duskin. This tells you anything, but I think there were other people. Okay, so roughly, yeah, so the simplicial nerve of this. Well, this could be any, say, strict two groupoid. So here we go. So N0, this is like supposed to be the objects. So it's just the objects. In other words, you'd be surprised, but even the one morphisms. Well, this is difficult to. This is. So up to here, it's like in the normal nerve. But with the triangles, that's already, right? So let me just say what N2 is. Well, what do you expect? So normally you have, yeah, so we have, maybe I should, for convenience, do this. So here you have two objects, gamma 0 and gamma 1. And my map, if you allow me, I'll write it the other way. Okay, well, what a triangle looks like this, I guess. So on each side, so here's gamma 0, gamma 1, gamma 2, G 0, 1. This is this thing, for some reason we tend to draw arrows from left to right and write everything in alphabetical order and the indices. It's just wrong. Should be either you do it from right to left or like in linear algebra. I finally realized what the point is. You have a matrix, you'll write, no, input is on the right. And so the multiplication comes out Aij times Bjk, like, Ik. So you have to do something. So G1, 2 goes this way, right? So this is right. And here we have, I guess, G 0, 2. Well, this is not, so normally, I mean, if we were in the station of normal groupoid, you would say just they commute and that's a triangle. But here, we will not assume that we have two morphisms. So here you put C0, 1, 2, right? Namely, C0, 1, 2 is a two morphism from, I guess, G0, 1 times G1, 2 to G 0, 2. Right? So this is the data. I mean, direct generalization of. Now, fortunately, there are no hieromorphisms. So as a consequence, actually to describe n, say little n, well, I cannot draw an n simplex, obviously, but basically it's like this. You have the n simplex. So here you have gamma 0, gamma n. Here you have maybe I, j, k. That is morphisms. Oh no, the other way. So Gij, jk. And the additional data, like before, there's a collection of theseCijks from normal Gij, Gjk to Gik. But now there's more space, so these are subject to a condition, which is like associativity, or I think this is like multiplication, I guess, and that is like associativity. Let me try. So condition Ci. So there are now 4 indices. C, J, K, L. That's C, I, K, L. C, I, J, K. Associativity. And this is it. Because we don't have any higher morphisms. Otherwise, I think this would turn into a complete disaster. Okay. Right, so this is pretty reasonable. Okay, so I invite you to check that. So if let's say I have the abelian case is useful to check. Right, so A abelian. Then this business is simply KAL1. Well, this is a space. So first of all, it's supposed, well, in my notation, this has negative degrees, so to speak, homotopy, because this is cohomological grading. So first of all, this is not going to seize the positive part of this, well, because this is not a space, more like a spectrum. Right? But then the negative part, if you actually check what all this says, well, if let's say, so in A, the only operation is addition, there's no exponentiation, it's all linear. And there's basically 2 things are cohomologous, if they are related like this, and this is a standard kind of fact. Right. Okay. Well, so do you have any questions? Just hoping to get a rough idea. So, well, so what am I supposed to show? Yeah, so I must point out that in principle this problem had been solved before, but not in this nice way. By mapping the sigma in this space into another much bigger space and showing that 2 maps are equivalences. But one would like, of course, to have, something reasonable, So it's my problem. So there is this concoction. So this is basically some kind of a super connection sort of on simplices, or forms rather. And this is, well, so this like has the algebra characters, so like group. Right? So what is this supposed to be, this map? So sorry, we will go like 10 minutes? Less, 15 even. Whoa, well, if I can introduce you to my notation then. This will be the first time new notation will be made public. So if you have any criticisms, all right? So, okay, well, what do you imagine this being? So first of all, again, abelian case. So this is known simply. Namely, this is this integral map from, well, this is basically the rational homotopy version of the Heidelberg-MacLane space. And who is this, a DuPont? Probably. or even before, right? This is, so here I'm assuming, I mean, this condition greater than or equal to -1. I mean, this is, right? And then there is this map. You just take forms, integrate on simplices. Right? We're talking cycles. So, and you get cycles. So this is, the, okay, so now, well, sometimes if you went with exponentiation, I mean, maybe, so why does this hold together? I think I could say, look, whole semester I was teaching vector calculus. So basically, no, I mean, 1, 2, or 3 variables max, right? So the high point of this is Gauss's theorem, which in our case actually, one could bring in the divergence term, but ours is 0 here. Oh. So this is, so the fact this is a simplicial map, a map of simplicial sets, is because of basic calculus. You know, the high point is that, or one can think maybe more differential geometrically, but then, you know, when you exponentiate, you write things multiplicatively. So in this case, because everything's a billion, you take your calculus, and you write, so basically, you write x vector calculus, you know, and everything's just fine. Why? Because, well, there's several points. Because everything commutes. Exponential over sum is product of exponentials. So that's no problem. And then it's the following fact about abelian connections, right? Well, this is exponential version of Green's theorem. So holonomy around the boundary is equal to the integral of curvature. Green's theorem, or if you want, Stokes. So so what to do in general. And this is where we come, this is very unpleasant. So basically you need to reproduce this in the following situation. That, well, okay, I have these Lie algebras, and they are not abelian, so the groups are non-abelian. I'm supposed to basically do group valued integration with values in a non-abelian group. This has several, I mean, as it's written, this simply makes no sense anymore. Right? Okay, well, this actually is, yeah, so this is, we're getting into the solution part. Yeah, so maybe roughly give you some idea. Right. So this map, actually, to start with, it's not difficult. This is, yeah, I mean, well, in the abelian case, so basically in the grid we have closed forms, great. Oh, no, even like functions. Then we have closed forms, so we can integrate, or maybe they have two values of them. The difference is boundary, great. Here, it's not so bad. So first of all, you notice that sigma 0 is equal to this nerve 0, and is equal to the same set. So of course you don't want to touch that, right? So this I0 is identity. So we did this exercise earlier, which I screwed up slightly, but basically in degree 1, the situation is that you have an ordinary differential equation, right? So you just solve, and this is called holonomy. But I mean, the one-dimensional connection is flat. Automatically, this issue doesn't even come up, right? So, yeah, so now, so we need integrals. So first of all, in the spirit of calculus, of course, you don't, there is a kind of a version of this where the target is a finite dimensional Lie group or something. And people have actually tried Riemann products. Those are Riemann sums. It's popular in the physics department. I mean, it's a lot of work. So then I learned from a paper of Kapranov that apparently the key fact was known to Schlesinger in 1928. Yeah, so like, it's not that. So of course we don't do the Riemann products. First of all, it's impossible because my Lie algebras are size of Herschel complex, but they are, on the other hand, nilpotent. So we define integral as the solution to a certain initial value problem, which you solve by your favorite iterative method, which doesn't just converge, I mean, it's finite. And everything else is done the same way. Right, so for instance, we have holonomy. And here comes the problem of notation. So my proposal was simply is normal integral, as you know, it is y is like this, it's a sum. Well, I just have P for product. It's convenient in that, you know, you go from A to B. Here you can also write AB, you know, in various other forms. You can write a double product integral, which becomes fortunately necessary. So I don't know, maybe there is a tradition for this, but they all try like variations on this theme, and it doesn't seem, I don't know, maybe what is not. My co-author, when he saw this, said that, you know, no way, but with time you get used to it. Right, so instead of this, we now, huh?
No choice.
No, he was planning to, because it's like, you have no idea. I mean, it takes some effort to produce a letter like this you can show. But once you do that, you know, just stick it everywhere, it's fine. Right? And he said, well, so it's easy to change. Never did. Oh, no, it's horrible, horrible. It's not horrible. I mean, you're just used to this. Well, you think this is beautiful. Okay, yeah, so for instance, we can talk about, I take a one simplex, and I have, remember we had this d plus b dt, like this kind of thing. And this makes sense. And what this is holonomy. Well, this is known to mankind. This is holonomy, basically, of this connection from, well, in my case, it's like, well, from the initial point, so from 0 to 1. So in the same spirit, we can have a double integral. This is more interesting. Maybe, okay, I mean, I can say precisely what I mean by this once. If I can do this correctly. Yeah, so forget that. Oh, man. Yeah, so basically, so I'll tell you what this is supposed to be. Connection in one variable. So this is, so you have the initial value problem like this. No, sorry, this cannot be A and B, this is x and y. It's a function of two variables. Right? Well, you have to remember, how do we define this? Well, it's of some. This is a function of two variables, obviously, such that derivative with respect to y is this, and the initial condition is y on the diagonal where y is x, you get, I know, 0. Well, here, if x is y, so on x is y, you get obviously 1. 1 meaning the ident element in the group. Because this connection has a values in this, the algebras. Right? And here is the little problem. I know this is probably bad notation, but let me. So I need to tell you what this is then. Oh, okay. And right, so solution is a function of two variables. It's not a function. It's like a group, it's group valued. But another problem with non-commutativity is that this, as it's written, is simply bad notation, but short. It doesn't mean what you think it means, because the group is non-abelian. But if it were abelian, it's what you think it is. I mean, to say that d log f is f over prime over f, or d of, it does make a lot of sense, and not just because you don't know which side to put it on, it's much worse than that. So in the abelian case, we just exponentiate calculus, so then to get back, you take logarithm, then you have normal calculus, and it's okay. This has all the, so this function has all the properties you might want. It composes from x to y, then from y to z, and so on. I mean, it's perfectly fine. But then, yeah, so this is it, more or less. So this maps to N1. This is this. And then we have to look at N2. Oh, but I don't want to do that. Really, but basically that data that I wrote out is like this. You have a connection, not flat. We have this family. You have a connection which is not flat, but its curvature is, roughly speaking, bracket with something that's given, and derivative of that something is 0. But in fact, you don't have to. If you want the right-hand side in Gauss's theorem, that this should be a central valued form, the derivative, and then you're still okay. But for us, it's so there's this. And if you can do sigma 2, you can do everything else. So sigma 2, I mean, there is my double integral, which I'm going to describe. And as far as I understand, so one can ask, what if the algebra starts lower, which happens? There is no candidate for this. This is defined. There is no reasonable candidate for the combinatorial side of any sort, although maybe there should be. Also, I guess, so basically, this extends to a simplicial map, which is very easy to show is an equivalence because by induction on nilpotency length and the fact that the abelian case is an equivalence. So if you want to know more about the details of this, you just have to figure it out. But in the infinity station, so all this uses is existence and uniqueness of solutions to initial value problems. No more. And basically standard differential geometry, including the definition of the double integral. And apparently known to Schlesinger back in 1928 because he wrote a paper. Well, it's not that my journal is so good, but I think the title consists of two words, like parallel transport and curvature. And he essentially understood this back then. Right, so I think I'll maybe finish with this. Oh, no, I can't. It's just a big formula with the, I can, where is it? Yeah, okay, well, no, it's not, it is, I mean, it's from calculus on Lie groups, which are not necessarily abelian. It's just, how do you do this? Well, actually, yeah, so, okay, so remember we had this exp. So I guess if I take an x in the Lie algebra, and then I have u, which is itself but in the group, right? It's easier to write. And the question is, for instance, forget the connection. The connection is d plus something. So what is this? Well, it's well known. I mean, this is homework. All right, so is it? So x add x, yeah, minus 1 over add x. This should look familiar, right? And you apply it to dx. I mean, maybe I should. Well, it's not great, but you see, in the abelian case, it simplifies a little bit. Well, this, yeah, considerably, I would even say. Well, this series starts with add x, so it's divisible by that, so, right? And then, so if nabla is what? And there is it, so if nabla is, yeah, so I mean, this is what I would, this is very bad idea, but I would call this d log. It is not d log, but if, in the abelian case, it is d log, as you know, but our log is very far from log, right? So nabla is like d plus, I know, a. Well, how do you imagine if this is d, right, and then nabla log u is, I guess, d, well, what I had before, plus a. No, because think about multiplying this on both sides by u. Then it says du plus au. So you divide by u, and you see this. Yeah, with the exception of the fact that this is this. Otherwise, like I said, I mean, for exponentiate calculus, you get this, and everything works. But and the rest is, you know, even worse than this. But there's a well, just calculus only groups. Yeah, well, yeah, so the fact that holonomy satisfies this, after some thought, is a well-known fact.
More questions? Is there some vector value for? No. Is there some vector value Stokes theorem for? You have.
Well, I can. Well, I mean, I see. In order for me to explain, I would have to explain notations. I have. I mean, the problem is that you have to start developing calculus from, you know, off the ground. There is a, by the way, I guess it's a volume, maybe an asterisk, even, I don't know where, by Amnon Yekutieli with the Riemann products. I mean, it's like this. And there's the combinatorial aspect and everything. The problem is that it's totally useless. I mean, if your Lie algebra is, you know, infinite dimensional, there's no group or anything resembling a Lie group. But he does Riemann products, I believe, for reasons. But yeah, so otherwise, you know, what do you do in calculus? So first you do, you know, one integral on an interval, right? Then you know, simplices. Then maybe boxes. Then you prove various theorems. So I can state some fact, and this is, I know he's not going to tell you a lot. Yes, we have not Stokes, Green's, I guess, maybe Green's theorem. I mean, the problem is that it would require going to like serious notation, and I don't really want to. I mean, it's not a good idea. Yes, I mean, okay. So, what does it look? Green's theorem. Yeah. So because okay, well, because of the non-abelian nature of this, some things were just like this minus that. That won't work, because you have to, you know, parallel transport has to be applied in order for addition to make sense, or multiplication. So looks roughly like this. So I have, well, rectangle, some surface S, two-dimensional. Right? So it's S boundary. So this is, so I have data which is roughly this connection in several variables, right? And then there is a form, a two-form, beta. If you remember, like in this piece in the Mercatile element, it's like this. So it's a two-form. So I can take, as a closed curve, I can take holonomy, oh no, sorry, P. Which is equal to, I mean, it's, oh, this is, oh no. Well, basically it says that it's, so for this pair, basically bracket with beta is the curvature of this. Right? There is a two-dimensional integral defined, which is, I mean, it's more or less like this. Well, there's a little, you have to multiply with the Gauss's theorem takes a very strange form, but no, I draw the nut because this is, I mean, it's all complicated by the fact that, well, I mean, this is like, if this is a rectangle, right, there are 4 paths separate. So but just to define this integral correctly around the broken line, this is worse than you think. It's not just, you cannot say sum, right? I mean, you have to conjugate, you know, some parts of it which are down the road, right? So it all grows in this sense. I mean, people have in principle done this. Well, they have the idea of a Lie group typically, and there's the whole calculus is not very new, based on even the Riemann products. So what it should look like, I mean, it's more or less known. Anyway, it was a pleasure. If you don't like my P, you can tell me later.